Hello, my name is Jennie Jorgenson, and I am an engineer at the National Renewable Energy Laboratory in Golden, Colorado, USA. Today I'm going to be discussing high-level considerations for long-term load forecasting over the timescale of decades. And I will be focusing on recent analysis using the country of Morocco as a case study. Morocco is particularly interesting to consider because they have aggressive renewable energy targets and a rapidly changing economy. So this implies lots of potential changes to the power sector and especially to demand, including deployment of technologies like distributed PV, air conditioning, electric vehicles, etc., which might make the power system of the future look quite different than it does today. So as I mentioned, long-term load forecasting attempts to capture trends in energy demand or consumption decades into the future. Obviously, this type of load forecasting is very important because often the resources required to address increased energy demand are capital intensive and take a long time to build, which includes generation and transmission assets. So getting load forecasts is very important, but it's really easy to either overestimate demand, which could lead potentially to expensive and unnecessary investment. Oftentimes that might be passed on to customers as an extra expense. While on the other hand, forecasts that underestimate future demand might lead to too little investment and perhaps possible shortages in the future. So in addition, long-term goals like renewable energy requirements or emissions targets can be dependent on future load. However, it is not necessarily easy to do a good long-term forecast since it's often dependent on many things. For instance, the gross domestic product, GDP, and economic drivers, the size of the population, the degree of electrification, and the diffusion of new technologies into the market. So these are all complicated factors and all interrelated complicated factors that can be difficult to forecast decades into the future. So given the strong connection between economic drivers and energy consumption, often the first step in long-term load forecasting is predicting trends in GDP growth. Growth in industries such as manufacturing and service can be very energy intensive, which drives up consumption. Additionally, as a country becomes wealthier, it can increase the energy intensity of individuals with technologies such as air conditioning. Electric vehicles may become more widespread, which can also obviously drive up consumption. So this graph shows Morocco as an example. The black points represent the historical GDP of Morocco through the year 2018, as well as three projections of GDP growth through the year 2030, low, medium, and high. The GDP of the country is predicted to be between 160 billion and 180 billion by the year 2030, which is clearly a considerable growth compared to today. So again, using Morocco as an example, we can see the relationship between historical GDP and peak and annual demand, which are the blue and red dots on this graph respectively. And then we can use regression to attempt to fit a curve to these relationships. In this case, we use two simple regressions, linear and logarithmic regression. The linear regression assumes that the relationship between those factors will remain constant into the future, whereas the logarithmic regression can be used as an alternative in cases where GDP growth may continue, but consumption could flatten out in the future. So this flattening may occur naturally as energy intensity for a country flattens with deployment of more energy efficient technologies, as well as through government or utility programs, such as energy efficiency measures and new building codes. So with only 11 data points on this plot, it's hard to discern a real difference between those different regression methods relating GDP to load, but all regressions illustrate, unsurprisingly, that an increase in GDP corresponds to an increase in both annual load and peak load. However, on the next slide, if we take those same GDP to consumption relationships and kind of zoom out to the three projected GDP levels that we were looking at 2 slides ago, we can see how both peak demand and annual consumption look in the 2030 timeframe. So although the 2 regressions look similar over historical values, as we saw on the previous slide, the 2 regression methods diverge for higher GDPs, with the linear regression predicting 20% higher peak in the high GDP growth scenario. But as I mentioned before, there's often, or there has been, a fairly well-established decoupling of load with decoupling of electricity demand with GDP, such that there's a flattening of the curve. Again, this trend may occur with deployment of energy efficiency measures, and therefore the logarithmic regression might act as sort of a more realistic load growth trend, but also could give utilities or governments an idea of the value of energy efficiency measures that might help to accelerate that decoupling. So, for example, in the mid-case scenario, the peak system demand difference between linear and logarithmic regression is around 1 gigawatt. So therefore, that kind of suggests that deploying energy efficiency measures or better building codes might help the utility or government avoid building that extra gigawatt of required capacity. So after computing the peak and annual energy consumption, the goal of demand forecasting is to better understand how to meet future system needs for planning the asset procurement that we were talking about before. If we build a prediction of the Moroccan annual load curve in 2030, using the monthly and hourly curves from a historical year, we can kind of see how the magnitude of the peak might change over time. So this plot shows the hourly load for Morocco for the year 2008, with darker blue indicating higher load. The plot indicates that the daily peak load occurs in the evening, kind of regardless of season, with a secondary peak occurring midday. July and August show the highest overall load, with the lowest load being in December and January. So again, if we take the historical load shapes from Morocco, such as the one on this slide, and then assume that the same load shape will persist in the future, even under higher consumption levels, we could see how things might look in the year 2030. So again, we know that we're neglecting significant factors that could change the shape of the load. It still provides sort of a useful basis for giving a more detailed bottom-up approach of what load might look like. On the next plot, we look at the average monthly load curve, which is calculated by averaging the same hour, 1 through 24, across each day in the month, as forecast for 2030. The peak load day in red is just the load curve that has load curve for the day with the highest demand in any single hour. And we can learn a lot from these types of curves. First, we know that the load shape is actually fairly consistent for most months with varying magnitudes. Secondly, the shape is fairly peaky. As I talked about before, there's 2 relative peaks each day, an absolute peak in the evening and a smaller relative peak in the midday. So this underscores the importance of attempting to perhaps flatten that peak, especially the evening peak, to preserve load factor efficiency. That will help minimize having to overbuild the system, that is, procure extra transmission or generation, and to ensure that the system is operating the most efficiently. And lastly, although it's a useful first step, we should address that the assumption of an unchanging load curve through 2030 is unlikely, given the rapidly industrializing nature of Morocco. Many economic effects can change the shape, such as mass adoption of air conditioning, deployment of electric vehicles, or perhaps distributed PV adoptions. Of course, not only does consumer behavior potentially reshape this load curve, but also government or utility programs, such as time of use energy rates or efficiency programs, that are also important to consider as a potential factor in changing load shape through the future. So as I mentioned, the shape of demand can influence power system operation, but so too can the shape of supply. In this case, Morocco has a very good solar resource, given its location. And as I mentioned at the very beginning, Morocco has a goal of procuring 52% renewable energy by the year 2030. Or the energy that comes from solar PV is an important consideration. So in particular, solar PV and concentrating solar power, CSP, are two solar technologies that are already being deployed in Morocco. But if we consider the case of zero marginal cost solar PV, which is typically dispatched first due to its lack of marginal cost, we could see that relatively low levels of PV penetration may actually align very well with the first midday peak that we discussed earlier in Morocco. But higher levels of PV deployment may start to show dramatic changes in the net load, that is load minus contributions from PV, which is shown on the next slide. So again, PV can have a dramatic change on the shape of the net load. So this is the load that must be met by the rest of the system resources. This has been sort of well documented in other areas of the world, such as sunny California here in the US and many other places. And due to its particular diurnal shape, that is sort of a low belly in the middle, a peak in the evening, it is often called the duck curve. So characterized by that particular animal. PV generation, like I mentioned, creates a new net load level in the middle of the day, which is different than Morocco's current system and might require backing down other sources of generation, and then a dramatic ramp up in the evening as PV generation decreases and the native load continues to increase. These net load shapes may present new challenges for the operation of the Moroccan power grid and should continue to be evaluated as Morocco moves forward. As an example, PV is a less expensive and a simpler technology, but using different forms of renewable energy, such as CSP, which I mentioned before, might have benefits such as integration with thermal energy storage and being a non-inverter based renewable energy generation type. So although CSP is significantly more expensive, it might become more viable with energy storage if it can help meet demand in the evening and nighttime hours with stored energy. So a key decision for the Moroccan Energy Ministry is to be able to decide the appropriate mix of these technologies, along with any other renewable energy options, to make sure that they have the right mix for their system so that they can meet their renewable energy goals. There are other ways to address changing net load shapes as well by preparing the system to better accommodate weather-dependent resources like PV. For instance, here is an example net load curve for spring in California, which has low load due to temperate weather, but still a lot of sun. So of course we see the familiar duck shape on this day. One option is to better allow the system to accommodate the solar in the middle of the day by enabling a very low load level, or duck belly in this example. And potential options for doing that include cycling down or turning off thermal generators in the middle of the day. By minimizing the number of other generators that need to be on, for instance, providing reserves, more solar can be used effectively rather than having to throw it away. Better solar forecasts can also help reduce the amount of operating reserves required, or allowing PV itself to provide reserves can also help. Other mechanisms may involve flattening the load curve by shifting demand patterns to better align with PV availability. This could be achieved with responsive demand, well-designed time of use rates, or even with energy storage. Other options include a diverse mix of renewable resources, that it's not over-reliant on PV, or the ability to exchange excess power with neighboring regions or utilities where possible. But ultimately, the cost of these possible mitigation options should be compared with the additional value unlocked by doing so. The value in the form of being able to more efficiently use the zero emissions resources on the system. And finally, I would like to conclude by reiterating the high-level main points of the presentation, as well as sort of more detailed ones on the next slide. First of all, I would like to reiterate that it is important to be able to forecast long-term load trends, but it's also challenging. It is important because the power system investments, such as generation and transmission, can be capital and time intensive, meaning they could take years to construct and bring online. So it's important to be properly planning. However, it's difficult to do since many factors influence electricity demand. These factors are complex, interdependent, and always changing, like the economic state of a country, size of the population, and the degree to which electrification technologies have diffused. We have discussed some considerations in this presentation, but a more detailed long-term load forecasting analysis may need to involve predicting consumer behavior, such as customer adoption of technologies like distributed generation, which could feed then a more detailed bottom-up load analysis that may better start to capture these complicated interactions. Another factor for long-term planning is that better understanding underlying demand can help integrating variable renewable generation, if that is a priority, and if further mitigation efforts will be necessary to help integrate those renewable generation sources. And lastly, for the more detailed key takeaways, I'd like to emphasize that, again, long-term forecasting is challenging, but perhaps the biggest impact comes from growth in GDP, which is why forecasting GDP is often the first step for long-term load forecasting. Logarithmic and linear regression models are often applied to relate GDP to demand, and often logarithmic regression show more reasonable expectations for where countries may be headed, given proper deployment of energy efficiency and building code regulations and technologies. We can use simple normalization techniques to estimate how hourly load may scale into the future. Although simple normalization does ignore several important factors, such as how technology may diffuse into the marketplace and thus change load shapes in the future. Variable generation such as solar or wind can also impact future load. In particular, solar can by reducing net load in the middle of the day, causing larger ramps as the sun rises and sets in the morning and evenings. And the next steps for here are more detailed bottom-up load modeling, which can better incorporate the impacts from changing load sources, including air conditioning, electric vehicles, distributed generation, in order to get a more complete picture of how load and load shape may change into the future, so that the utilities and countries can better plan for their future. Thank you.